Hi everyone, I'm Jinyu from Shanghai Jiao University. Our system is named Pisces. It is a software transactional memory built upon non-volatile memory and aims to achieve both read efficiency and high scalability. Non-volatile memory such as PCM, IRAM, and 3D Point is revolutionizing the memory storage hierarchy. The recent release of Intel Optane persistent memory marks the transition of NVM technology from research prototypes to mainstream products. NVM is byte addressable and has low read latency, but about 10 times write latency. To efficiently program on NVM with a balance among good programmability, high performance, and low software overhead, the persistent transactional memory has been exploited by priori work. Through combining the transactional memory and NVM, PTM offers the properties of atomicity, consistency, isolation, and durability. But most of existing PTM systems neglect the performance of read operations or have scalability issues. The root cause for the read deficiency problem is that such PTM systems expose high NVM persistence overhead to readers. In such systems, to modify an object, a transaction will first lock the object and record the modification log. After flushing the log into NVM, the transaction can update the object. Finally, it will flush the updates into NVM and release the lock of the object. However, this may block concurrent reader operations on the same object. This long blocking duration may become a severe performance bottleneck due to the amplified persistence overhead incurred by high write latency of NVM. Another related work hides the NVM persistence overhead through eliminating the flush operations in the execution threads. It leverages the background threads to asynchronously flush writes to NVM. Such PTM design duplicates the persistent objects in DRAM, and the foreground threads only updates the objects in DRAM, and one background thread is responsible for updating the objects in NVM. However, the background thread has to apply the logs to the persistent objects in a total order according to the monotonic increasing transaction ID. Because the background thread cannot tell whether these two transactions have dependency, such a strict persistence ordering harms the scalability once the background thread cannot catch up the pace of the foreground threads. So overall, it is challenging to design a PTM system that insulates readers from being affected by the high NVM persistence overhead while avoids overly constrained persistence ordering simultaneously. We notice that snapshot isolation can avoid rewrite conflicts and surfaces for many real-world applications, which makes it possible to design a PTM that allows a transaction to persist its logs in the critical path instead of in the background, while hiding the high persistence overhead from concurrent read operations. Usually, multi-version concurrency control is a common choice to achieve SI. We observe that the redo logs, which will be finally applied to the durable data, can be reused as the new data versions, which enables us to efficiently introduce MVCC to PTM. A following question is that, can an intuitive MVCC-based PTM satisfy our goal? To answer this question, we implement a prototype MVCC PTM. Like a common MVCC design, we maintain an identifier and a version list for each object. A write operation will insert the newest version as the head of the version list, and a read operation will locate the correct version to read in the version list. However, we find this intuitive design still has considerable overhead for read operations because of the following two issues. First is the read indirection problem, which leads to extra random memory accesses. Take a linked list as example. If a transaction traverses this three-object linked list, A points to B, B points to C, it actually needs to traverse a much longer list, which at least contains 3 objects and 3 object IDs. The second problem is read operations may still be blocked by the NVM persist operations. Specifically, when reader accesses an object which is being locked, the reader may be blocked until the writer commits. As an example shown on the right, T1 starts with timestamp 5 and it wants to read object D, while T2 locks the same object. Here, T2 may commit D4 or D5, so T1 must be blocked instead of directly reading D3. So to eliminate the cost of extra dereference caused by object IDs, Pisces keeps up to 2 versions for each object. Similar with the MVCC design, a writer on an object will create a new version and thus can proceed with the concurrent readers. The difference is that the writer will eagerly override the old versions with the new versions, which makes an object usually have only a single version, and thus the readers can directly get that version without extra memory dereference. To reduce the blocking overhead in the intuitive MVCC design, Pisces proposes a 3-stage commit protocol to decouple different functionalities of the whole commit phase into different stages. Hence, only the writers in the second commit stage can block concurrent readers, and the second commit stage only involves 2 DRAM writes. Pisces can allow nearly non-blocking reads. Now let's see how Pisces executes transactions. Pisces maintains a global timestamp, and each transaction retrieves this timestamp as its start timestamp in the beginning. For each data object, Pisces attaches a header, which is used as the write log to coordinate concurrent writers on the same object. And when an object is locked, it will point to a new version. Suppose a transaction T wants to write object A. It first gets A's log, and then make a copy in its own log. After that, the transaction T can update its copy. Also, a transaction writes other objects in a similar way. For read-only transactions, Pisces directly commits them without any operation. While for read-write transactions, Pisces commits them through 3-stage commits. In the first stage, persist stage, a transaction has to flush the object copies in its log to NVM. A transaction reaches its durable point at the end of this stage because its logs is durable and will be redone after crash. In the second stage, concurrency commit stage, the transaction atomically makes object copies visible to others. After this stage, the object copies in the logs are regarded as the second versions for objects. So the end of this stage is a commit point for transactions. Then how does Pisces achieve the atomicity? When allocating an object copy, Pisces sets the copy's version pointer to the transaction's end timestamp. And in this second commit stage, the transaction's end timestamp will be set to the global times +1. Thus, all the object copies are assigned a same validate version number at the same time. After that, the global timestamp will be increased by 1 in order to make all the new versions visible to other transactions. In the last commit stage, write-back stage, Pisces firstly leverage the idea of RCU grace period detection to ensure the original objects, such as object A and object B here, are no longer needed by others. And then Pisces eagerly writes back the new versions to let readers directly access the objects in the home location without extra memory accesses. Finally, the objects are unlocked for following updates. TM read is used for reading objects, and it has both fast pass and slow pass. When an object is unlocked, which means there is no concurrent writer, TM reads executes the fast pass, which simply returns the object. Otherwise, in the slow pass, TM read compares the object copy's version number with the transaction start timestamp to decide to return either the original object or the object copy. Okay, that's all about the transaction interfaces designed for applications to use. For other designs like how to reduce NVM writes, please refer to our paper. We conduct experiments on an Intel Xeon Go server with real NVM equipped to demonstrate the read efficiency and scalability of Pisces. We compare Pisces with DUDETM, which is a state-of-the-art PTM system. In the micro data structure benchmarks, when the update rates are low, the throughput of both Pisces and DUDETM can scale well with the increase of the thread number. Note the y-axis is log scale. Nevertheless, owing to the read-friendly designs, Pisces has higher throughput. In TATP, which is a read-dominated OLTP benchmark, Pisces also outperforms DUDETM. From the figure on the right, we can see Pisces obviously decreases the read latency compared to the intuitive MVCC design, thanks to no extra memory access. Pisces also show better scalability than DUDETM. Recall that if a background thread needs to persist updates to NVM in a total order, it can harm the scalability, and DUDETM represents such design. In the hash table benchmark, each write transaction only updates one object, so the background threads in DUDETM can timely finish the persistence operations when the thread number is no longer than 16. However, if adding more threads, the scalability issue comes up. In the testing for TPC-C new order transaction, each thread has a warehouse and all the transactions are write transactions. DUDETM cannot scale because such transaction generates much more logs and the background thread cannot catch up the pace of the foreground threads. In contrast, Pisces can also scale much better. So to conclude, this talk presents Pisces, a read-friendly PTM that provides transactional memory APIs for programming on NVM. With several techniques such as DVCC and three-stage commit, Pisces achieves both read efficiency and good scalability while ensuring snapshot isolation and crash consistency. Thank you for your attention. I'd like to take questions.
Okay, I like this is very nice work, and I like the idea of the three-stage commit and dual version concurrency control. But the one potential downside of the dual version concurrency control is the lack of the versions, right? So, for example, in the case of the workload is write intensive and write is very skewed, then the same object version of the number of versions for the same object can be grows very quickly. Then I guess the Pisces have to wait until reclaim the previous versions, right? Is that the could be the potential performance bottleneck?
Yes, since currently, since we design Pisces is for read-dominated workloads, so finally Pisces is a read-oriented PTM. It's in some write-dominated workloads it cannot perform well, I think, but maybe in some write most workloads, such as in this experiments, we use TPC-C new order transactions, and the update rate is 100%. Pisces can also perform well.
Okay. Any other questions? Okay, if there is no question, let's thanks to speaker once again.